We are now interested in understanding the very important physics concepts known as impulse and momentum. And the big idea about momentum is that it is associated with what we call conservation, meaning the total quantity stays constant, does not change. That will need to be developed a little bit more, particularly because what we're talking about is that being true in an isolated system. If ever a time comes where it seems like the total quantity doesn't remain constant, then we have not properly identified the system that's interacting. There, I just spilled the beans right at the outset. Three actual conservation laws in nature of import or momentum that we're studying now. Total quantity before equals total quantity after. After what? After an interaction of some sort. There's the conservation of energy. Means that all the forms of energy are constant. That's a huge one there. We'll study that after this little unit on impulse and momentum. Conservation of electric charge means that there's equal quantities, equal numbers of positive and negative charges in the universe, which is really important because if it was not true, then very quickly, since the electromagnetic force is a trillion times stronger than the gravitational force, the electromagnetic forces would dominate in the universe and we wouldn't have stars, planets, and people. So be thankful that we have conservation of electric charge, that we can't change the total quantity, and that they're about equal. So the symbol used for momentum is rho, R-H-O, so to speak. It's a Greek symbol. A little bit easier to write than a P, at least for me, because it's just one little, little swoopy thing here. All right. Anyway, then we use the primed and unprimed notation to denote before and after. So unprimed is before, just written without apostrophe, basically. Primed is after an interaction, written like this. So we put the little apostrophe symbol. And that's the definition of the symbol. And now to define some key features of momentum. Impulse and momentum. They are related to each other, and they're related through Newton's laws as well. It's probably not too surprising. In fact, Newton formulated his second law of motion through the concepts of impulse and momentum. A little more on that later. Momentum is always conserved in an isolated system. So that's the key. It must be isolated. And the conservation principle for any number of objects, the total momentum before equals total momentum after. So that's kind of redundant a little bit, but let me write in symbolically what that says. Rho sub t, total momentum before, equals rho prime sub t, total momentum after. And in the special case of two objects, which will be a typical case for us, we have the changes in momentum. There's changes in momentum that occur between two objects interacting, okay? But if we assume that the two objects are the system, and that's all that's in the system, then they're equal and opposite. The changes are equal and opposite. So the total amount is unchanged. So change in momentum 1 is minus change in momentum 2, namely object number 1 and object number 2. Notice up here, there can be any number of objects. Okay. Then the velocity of the center of mass of a system of particles interacting is constant in an isolated system. And no matter what happens, so you can, for instance, have some kind of bomb that's flying through the air, and it explodes, and the velocity of the center of mass of all those various pieces is constant. And then Newton's third law follows from the conservation of momentum as well. Action-reaction. Force and time, particularly. Okay. Basic definitions. We have momentum. And it's a property of an object in motion. Moreover, I would like to think of it as The strength of motion, another way you can think about that is the stopping difficulty. So there's a variety of things that are hard to stop. You could probably imagine that a slow-moving train is hard to stop, but so is a high-speed bullet. Both can have a significant amount of momentum. More than likely, it's the slow-moving locomotive that has a greater amount, depending on just how slow it is. But in any case, if you try stopping various objects, the strength of motion essentially depends on two things, or the stopping difficulty is dependent on two different things. Oh, what are they? They are implicitly stated, actually explicitly, if you were listening to the comments on the train and the bullet. Namely, mass. A lot of stuff in motion. So that's the train. You got a lot of stuff, you got a lot of inertia. Once moving, it wants to stay moving. The other thing is the speed. So the velocity or speed. And we'll kind of stick with the velocity because the nature of momentum, it is a vector quantity. So turns out that momentum is defined as the product of mass and velocity. So that makes it pretty easy. It's just mass times velocity. Okay, so far everything is intuitive, right? So the symbol is rho, the formula is rho is mv, and you will notice now that I put the hat or the arrow on top of the symbol to denote the vector nature of it. Units, we'll see mass is kilograms, velocity is meters per second, so kilogram meters per second. It doesn't have its own nice unit as some physical properties do, like energy, which is in joules. This doesn't have that. So there it is defined. So as mentioned, momentum is a vector, and so let's just reiterate or review what that looks like, how to deal with the vectors. So say we have an object, number 1, that has a vector quantity of momentum looking like this, size and direction. Object number 2 looks like this. What's the total? Well, if you want the total, you just add the two. Number 1 plus number 2. So here we go. I added tail to tip 1 onto 2, and there it is. And to get the resultant, unconnected tail of the first to unconnected tip of the last, there's your resultant total momentum. Now let's take the same two momenta, but this time they mean different things. This time I have momentum. Here's the momentum of something. It could be multiple objects as necessary, but probably not. And then afterwards, this is the momentum here, afterwards. So it's not momentum of object 1 and object 2, but it's before and after. So it's probably, since they're different, probably it is not the whole system. In fact, definitely it's not the whole system. Because by the whole system, I mean the whole system that's interacting. And if there's nothing else interacting, then it's got to be the same before and after. So what we're most likely referring to here, even though I'm not explicit about it, is this is an object's momentum before interacting, and after interacting, it's changed. Now something else has changed, equal and opposite, but that's not the point at the moment. What is the change in momentum corresponding to this before and after picture? Well, change is final minus initial. So here's the final, here's the initial. Let's subtract them. And to do that, we connect the tails together like this and connect from old to new on the tips, subtrahend to minuend. So we're going to go from here to here. Simple as that. That is the change. Notice how much different the change looks than the total quantity. In any case, basic vector principles there. And that's how you can handle, graphically at least, intuitively, total, momentum, and changes in momentum. And next video we'll look at the idea of impulse.